Hello everyone, today we're going to do another example question on calculating regarding towards equilibrium constant. Okay, so for this situation we're talking about is that we know the equilibrium constant. Okay, so we know Kc, and then we also know the initial concentrations. For concentration, we use brackets to represent it, and I'm going to put a lowercase I represents the initial concentration. And we're looking for equilibrium concentrations. Okay, so that's what we're looking for. Bracket EQ represents equilibrium concentration. Okay, so that's the situation. Now let's read the question, see if we could recognize this questions about that situation. Okay, so now let's see one more time. So from here we know Kc, it's given right over there. Okay, so Kc, so given Kc equals to 0.1. okay, and then let's see what else we know. So initially we have the two concentrations, so those two will be the initial concentration. So I'm going to use the lowercase I to represent it. So it's going to be 0.2, and initial concentration for oxygen will be 0.2 as well. Okay, and then you're looking for the equilibrium concentration of the reactants and the products. So you're looking for the equilibrium concentrations. Okay, so we're trying to find the concentration of reactants and products will be EQ, O2, EQ, and NO, EQ. So those are the things we're looking for. Okay, so for this type of calculation, we need S table. Okay, we need S table to help us to figure out the relationship. Okay, so now let's start from expressing Kc, because that's always helpful. Okay, so let's see Kc equilibrium constant. Okay, so for Kc is equals to, no matter what, doesn't matter which direction the reaction goes, always will be the use, if we consider this forward direction, that the products, the substance is on the right side of the equation. So that will be the products. So always is going to be the substance on the right side of the equation to its raised to the power of its stoichiometric coefficient. Okay, and then over the reactants, the substance is on the left side of the equation. Here just 1. Okay, and then O2 multiply the concentration of O2 is 1 as well, and then everything in this expression, because we use K, that's equilibrium, is at equilibrium, so every concentration in this equation will be EQ, and EQ. All these three terms we're looking for. However, we do know the relationship after this expression, the equilibrium constant, we know from the question it's given as 0.1. Okay, so the next thing is, okay, so we express it, and then we said we need S table to figure out the relationship. How we're going to have at least a variable will be involved in this expression, then we can calculate for it. Okay, then we'll know the rest. Okay, so now let's set up S table. Always I would encourage you to have your balance equation with you on top of your S table. That's going to help reminding yourself what's the stoichiometric coefficients relationship between the reactants and the products. Okay, so then it's going to help you figure out the change. Now let's set up a table, then we'll talk about the table for a second. Okay, so for this table, okay, again it's S table that represents what? ICE. I represents initial, C is change, E is equilibrium. Okay, the whole table we're talking about based on molarity, because we're talking about concentration. Okay, so that will be N2 concentration, O2, and NO concentration. Okay, and then let's put the information in the ones we already know inside this table. So we know the equilibrium, the initial concentration of N2, which is 0.2. Same concentration for O2. Okay, and then for nitrogen monoxide, it's going to be 0. It's actually implied because initially you only have the reactants, you don't have no products, so that's going to be 0. Okay, so those are the information we know, and the rest of the table we need to fill out. Okay, and then the other thing is you have to know, you have to first calculate Q. Okay, so that's very important because it's going to help you to figure out which direction the reaction goes. Okay, so now let's express Q. Okay, so Q is what? Reaction quotient that represent, we can use it to express at any moment for this reaction. Okay, so we don't want to know. So with given information, again, we know it's initial, we only have reactants. So by logic, we know the reaction is going to go forward direction, go to make products. However, we also can use QC to actually show us mathematically. Okay, so let's see how we're going to do that. So QC is the same expression, however, now is also products raised to the power of its coefficient and over reactants. However, in this expression, it's not going to be EQ anymore. It's just at any moment. And then in this, we consider as initial. Okay, so let's put the I as lowercase. Okay, so now let's put the numbers in. So it's going to be 0. And then it's going to be 0.2 times 0.2. Okay. So all this, we put the numbers in, this equals what? 0. Okay, so QC equals to 0. Now what's the next step we need to do to actually figure out which direction the reaction goes? Yes, we need to compare QC and KC. Okay, so QC, which is 0, and KC is given from the equation 0.1. So QC is smaller than KC, then reaction goes the forward direction, gonna produce product. Okay, and then one more time, for KC, equilibrium constant, can you have a negative number? No, you'll never have a negative number. It's always going to be a positive number. And then the matters if it's a really small positive number or it's a big positive number, it's going to help you to know which direction the reaction goes. Okay, so anyway, so in this case, once you have a 0, then no matter what, the reaction is going to go to forward direction because you know that KC is now going to be negative. Okay, anyway, so go forward direction. The QC and KC relationship helps us to figure out the direction of the reaction proceeds, and it's gonna help us to figure out the change. Okay, so based on this reaction, every 1 mole of N2 gonna react with 1 mole of O2, give us 2 mole of NO. Okay, so that means if reaction goes to forward direction, so you're gonna consume the reactants and make product. So when you consume reactants, that the change is gonna be negative sign, right? It's gonna getting less, and then the product is gonna be positive because you're making product. And what's the ratio? What's the changing ratio? Is 1 to 1 to 2. So if we assume that every negative 1x, so every 1x of NO N2 you use, of course you have to, that's 1 to 1 ratio, then you have to use a negative x as well, and then you're gonna make how many x of NO is 2x. Okay, so it's gonna be 2x NO produced. Okay, so that's the change, and this is the part quite important for you to understand, otherwise the whole table is gonna get messed up. Okay, so after this step, you can fill out the last piece. Okay, so the last piece is quite easy because it will be just, we are looking for equilibrium, we can consider as final. Okay, so remember before when you're calculating change, right? Change is always equals to what? Equals to final minus initial. Okay, so in this case, we are looking for final. Okay, so then how do you look for final? You move the initial onto the other side, so final is going to equal to initial plus change. So you're going to use 0.2 plus negative x, so then turns out to be just 0.2 minus x. Same way over here, 0.2 minus x. This will be just 2x. Okay, so now we use one variable, which is x, express all 3 concentrations at equilibrium, and then we know the relationship with them equals to 0.1. So now the only thing we need to do is plug all these expressions into our KC. Okay, so now we're gonna do that. Okay, so now let's do this. Okay, so you have KC. We already know it's over here, the expression. Okay, so it's this one. Okay, so KC equals 2 NO squared, so you have 2x squared. On the bottom denominator, have 0.2 minus x times 0.2 minus x equals to 0.1. Okay, and now from here we'll be just solving this equation. Okay, so now let's see what's on the denominator. Actually, it's what? It turns out to be 0.2 minus x squared equals to 0.1. Okay, if we have the square on the numerator and also on the denominator, now you can do a square root on both sides, so you can get rid of that square. Okay, so that's easy to do. So now I'm gonna do a square root. Okay, so I'm gonna square root, so that will be 2x squared 0.2 minus x squared square root for 0.1. Okay, so after do this, and then on the left side simplify into 2x 0.2 minus x equals to 0.316. Okay, at this moment we'll be just cross multiply and solving for x. Okay, so that will be 2x equals to 0.316 times 0.2 minus x. Now you just need to distribute that 0.316, multiply this one, multiply the x. Okay, so after you do that, and then you will have 2x equals to 0.0632 minus 0.316x. Now you're going to move the expression with x onto the left side, so you reorganize this equation. After you do that, it's going to turn out to be 2.316x equals to 0.0632. Okay, so that's what you have, and solving for x, the x will equals to 0.027. Okay, so now you have the x value, and we're looking for the equilibrium concentrations. So we're looking for all this, and now you know the x value, so we're just gonna plug in the x value right inside there, and you will get the concentrations for each reactants and products at equilibrium. So you will do that. So then the concentration for the product at equilibrium will be 2 times x, 2 times 0.027, turns out to be 0.054. Okay, and then the other two reactants will have the same concentration, and you plug in will equals to 0.2 minus 0.027, turns out to be 0.173. Same concentration for O2 will be 0.173. Okay, so this will be the answer for this question, and then this is how you solve this type of question. Okay, so again, the thought process will be, you know the equilibrium constant, you know this Kc, you know the initial concentrations, and you're looking for the equilibrium concentration. Okay, and then what do? We know, first of all, we need S table, and the next thing is you have to fill out the table, express QC, okay, and then calculate QC compared to Kc, and you know which way direction goes, which gonna help you determine the change, so you can determine the sign in this table. Then you'll be able to express the equilibrium concentration, then put back into the expression for equilibrium concentration. Then you'll be able to solve the x, and then therefore you'll be able to solve the whole question. Okay, so this is how you do this question, and then that's it for this video. Thank you for listening.